Swayam Prabha. Digital India. Educated India.
Hi everyone. In the last few lectures, we discussed about Hilbert spaces. From today onwards, we are going to discuss about operators between Hilbert spaces. Okay, so let us start with the definition of a linear operator or linear transformation. So let us take V and W to be vector spaces over C. Throughout the course, we are going to look at vector spaces or Hilbert spaces or complex field only. So we say a map T from V to W to be linear if the following conditions are satisfied. The first one is T of x plus y equal to Tx plus Ty for every xy in V, and the second one is T of alpha x equal to alpha times Tx for every x in V and for every alpha in C. So that the two conditions says that T preserves the linear structure of V. The first condition says that T preserves the addition of two vectors in V, and the second condition says that T preserves the scalar multiplication. So we can say that T preserves the linear structure of V. So one immediate observation after defining a linear transformation is the following. If T from V to W is linear, then we can say that T of the 0 vector of V, that is 0 suffix V, is nothing but 0 vector of W. So that can be seen from the second condition. You take alpha to be 0 and x any vector, then alpha into x is 0. So T of 0 W nothing but 0 times T of 0, T of any other vector x. So you will get 0. One other important observation is the following. Suppose let us take x1, x2, so on, xn in V, and alpha 1, alpha 2, so on, alpha n. These are the complex numbers. Then we can say that whenever T is linear, T of alpha I xi I equal to 1 to n is nothing but summation I equal to 1 to n alpha I T xi. This directly comes from the two properties 1 and 2, the axioms of linear transformation. We have to apply 1 and 2 for n many vectors. Okay, so this is the observation we will be using at a later point. Okay, let us look at simple examples of linear maps that we have already know. Let us take lambda to be a complex number and V be a vector space. All the time we take vector spaces over C only. So define T from V to V by T of x equal to lambda times x for every x in x, and anyway lambda is fixed. So this is nothing but we can write this t as lambda times the identity operator. When lambda equal to 1 we will get the identity operator. When lambda equal to 0 this is the identity operator. When lambda equal to, so this is lambda equal to 1. When lambda equal to 0 we get t to be 0, the 0 operator, which sends every vector of v into 0 vector of v. Okay, so it can be easily checked that t is linear. This is a trivial example. Let us look at some more examples. Okay. So let us take two natural numbers m and n with n less than m. Define t from Cn to Cm by t of x1, x2, so on, xn equal to x1, x2, so on, xn, and 0 in the remaining components. So there are remaining components are m minus n, because m is bigger than n. For every x1, x2, so on, xn in c power n. So we can easily show that this map is linear. Check that t is linear. Here we are identifying Cn with t of Cn. There is a one-to-one map from Cn t of Cn, and we can identify again this as subspace of c power m. So t of Cn is a subspace of c power m, so which is included in c power m. So for this reason we call this map to be an inclusion map. Okay, let us define one more map from Cn to Cn. Define t from Cn to Cn by t of x1, x2, so on, xn as x1, x2, so on, x n minus 1, comma 0 for every x1, x2, so on, xn in c power n. We can easily check that this map is linear. Some more important examples that we will be using again and again. Define, so let us call this as R from L2 to L2. Here L2 is nothing but L2 of n. If you don't specify anything, it is L2 of n. So define by t of x1, x2, x3, so on as 0, x1, x2 for every xn in L2. Again this we can check that this map to be linear, and this map is known as the right shift operator. The reason for this is that it is shifting one unit to the right every time, so that's why it is called the right shift operator. So this is called okay. So this is also known as the unilateral shift operator. On L2. We will see why this is called unilateral shift operator at a later stage. Okay, so the conclusion is that we can easily show that this map T to be linear. We can easily check that T is linear. Okay, so these are few examples. Okay, now one thing we can ask that, let us fix a notation for linear maps. So we denote the set of all linear maps from V to W by LVW. So set of all T from V to W, so that T is linear. That means LVW is a set. Now the question we can ask is that, is this set LVW non-zero? We can always say that we can define a zero map from V to W, sending so zero map we can define from V to W also. Earlier we have defined from V to V. So here we can send every vector of X into 0 of W. This is also a linear map. So this LVW contains 0 map. Now question is, can it contain a non-zero map? That means if V is non-zero space and W is also non-zero space, can LVW is non-zero? This is the question. When V and W are finite dimensional vector spaces, this can be done easily. Answer: if V and W are finite dimensional spaces, then we can say that LVW is non-zero. When V and W are finite dimensional, we can since V is non-zero, you can fix a vector, fix X in V and Y in W. Now V as a basis, extend let us take X to be non-zero and this Y is also non-zero. Now get a basis which contains X as one of the basis element. Similarly, get a basis for W which contains Y as one of the element. Then you define a map which sends basis elements to basis element, and you can check that that is a linear map. So in that way we can actually get a non-trivial or non-zero linear map from V to W. Now the question is that what will happen if V and W are infinite dimensional? So you can try this one. If V and W are infinite dimensional, can we say that is the question. That means you fix a vector x non-zero vector in V and fix a vector y in W which is non-zero. Can we find a map, linear map which sends x into y? So this is another way of, if x is in V and y is in W, so fixed vectors then does there exist a linear map T from V into W such that T of x equal to y? If we can answer this question, then we can conclude that LVW is non-zero. This is one way of answering the question. There may be another ways also, because our aim is to show that we should get a linear map which is non-zero. In the Hilbert space setting, this question can be answered in an easy way. So let us look at if H1 and H2 are Hilbert spaces, both are over C and both are non-zero, then we can say that L of H1 H2 is always non-zero. Okay, so let us fix some non-zero vector x in H1 which is non-zero and y is in H2, y is non-zero. We can find a map, linear map which sends x into y. So without loss of generality, we can assume norm x is 1, assume that norm x is 1 in the Hilbert space 1. Okay, now define T from H1 into H2 by T of Z is nothing but inner product Z with x multiplied by y. Okay, for every Z in H1. Now we can easily show that T is linear. Check that T is linear, and also T of x, if you take, that is inner product of x with x multiplied by y, but this is nothing but norm x square into y. You know that norm x square is 1, so this is y. That means we can the conclusion is the following: this L of H1 H2 is non-zero whenever H1 is a non-zero space and H2 is a non-zero space. In the case of vector spaces also, the result is true. That means LVW is non-zero, but we have to take two non-zero vectors x in V and y in W respectively and find a map which sends x into y. In the Hilbert space setting, this is very easy. Okay. Next we want to discuss about the structure of L of H1 H2. That means can we say that we can define more operations on this L of VW or L of H1 H2 so that it becomes vector space? Then we can ask whether it has some more properties. So the next thing we can discuss is that, so on LV double, so define, let us take two elements from LV double, T and S, and define Ts at x. T plus S at x is nothing but Tx plus Sx for every x in V. So we are taking, so when we say on, so let us take S and Tr from LVW, define this as addition of two operators. Then alpha times T at x is nothing but alpha times Tx for every x in V, and alpha is in C. With these two operations, we can check that, show that this is a vector space. It is trivial actually. So sum of two linear transformations or linear maps is linear, and if you multiply a scalar with a linear transformation, that is again linear. So from that we can conclude that it's a vector space. Okay. Now apart from this vector space structure, whether LVW has another structure. So obvious thing we can think about is a multiplication of two operators, but we cannot define multiplication of two operators when S and T come from LVW. So if we have V, W and some other space Z, if you take, and S is a map from V to W, T is from W to Z, then we can define T composition of S at X is nothing but T of Sx for every x in V. So we can easily check that this composition of these two maps is linear, and T composition with S is a map from V to Z. But if you want to look at powers of an operator, we cannot take maps from V to W. In that case, we have to look at maps from V to V only. So for that reason, we want to look at maps from V to W, sorry, V to V. Let us fix a notation. Instead of writing LVW all the times when V equal to W, so we write this as LV instead of writing L of VV, where V is a vector space. Over C. This is for simplification of the notation. Okay, so on LV we can define composition of two operators. So if I take S and T coming from LV, so S composition T at X, the same way whatever we have defined. We already know that LV is a vector space, and we are defining a new operation called multiplication of two operators or composition of two operators. So we can actually say that with these operations, if you look at the set LV plus, and this dot is a scalar multiplication, and this is circle is the composition of two operators, we can say that this is an algebra. What is the meaning of algebra? Algebra is a set with three operations satisfying the properties that we stated for LVW. So let us look at the definition of an algebra. Let A be a non-empty set, then A is called an algebra, if A plus and scalar multiplication is a vector space. So here again we are going to look at over C. The second condition is A plus circle, that is a composition in the case of LV. So this is nothing but multiplication of two elements from A. This is a ring, and the third condition. So if you observe these two axioms or these two properties, plus is there in both conditions. And the first one, in the first case we have scalar multiplication, and in the second case we have multiplication of two elements from A. So if we can connect these two operations, dot and circle, then we can actually say that there is a relation between among all the operations, these three operations, plus, dot and circle. So we say that all these operations are compatible with each other. So such a condition is given as follows. If you take a scalar alpha dot A, this is one element in A, and if you look at another element B and take multiplication of these two elements alpha A and B, this should be A circle alpha B, and this is nothing but alpha times A circle B for all A B in A, alpha in C. So the third condition connects the earlier two operations, scalar multiplication and multiplication of elements of A. So if a set having these three properties, if there are three operations and satisfying all these three properties, such a set we call as an algebra. Okay. If the field is complex, we call the algebra to be complex. If the field is real, we call the algebra to be real. But in our case, we are going to look at complex algebras only. Okay. Now we have a ring structure here apart from the vector space structure. If the ring is commutative, we say algebra to be commutative. So definition: if A plus dot circle is an algebra, such that the ring A plus circle is commutative, then we say that A is called a commutative algebra. In other words, A circle B must be equal to B circle A for every A B in A. Okay. So if there exists an element A in A such that A circle E equal to E circle A equal to A for every A in A, then we say that this element E, then E in E is called a unital element, or it's also known as identity element. In A. So if A has a unit element or unital element, we call that algebra to be unital. So in algebra, A with unit E called a unital algebra. most of the time we'll be looking at unital algebras only. There is a way of getting a unit for a non-unital algebra. So that process is known as unitization. That we'll be looking at a later stage. Okay. So once we have a unit element, we can define inverse of an element if A is an element of an algebra A. So let us take A in A. So if there exists B in A such that their multiplication equal to the identity element, then B is called an inverse of A, and it is denoted by A inverse. And here we can show that the if there is a unit, it must be unique, and similarly inverse, if at all, if it exists for a element, that must be unique. Show that unit element is in an algebra is unique. The second observation is that if A is an inverse, then it must be unique. This is very well known from properties of rings. Okay, so for this reason we always say that the unit and the identity element and the inverse of an element. Okay, so these are some definitions of algebra and the elements in the algebra. So one simple example of an algebra, as we have already pointed out. So let V be a vector space over C. Then we can say that LV is an algebra. Here multiplication of operator is nothing but composition of two operators. The second example we can look at is, let S be a non-empty set. So denote or define B infinity of S C, set of all functions from S to C such that they are bounded. F is bounded. So we know that this B infinity SC is a vector space when we define F plus G at a point X as Fx plus Gx for every F and G coming from B infinity of SC. X is coming from S, and alpha times F at X is nothing but alpha times Fx for every F in B infinity SC, and alpha is a complex number. With respect to these two operations, we can check that this is a vector space, and the multiplication we can define is F circle G. Here this is not composition, this is pointwise multiplication for every X in C. Sorry, X in S. Then we can easily check that this B infinity SC is an algebra with the above operations. here don't confuse with this composition. This is not composition symbol. This is product of two elements in B infinity. Okay, so from now onwards we use this notational convenience. So or we can say it is convention. We write AB instead of a circle B for elements AB of A. A is an algebra here. Okay. In fact, we can give more examples. One more example we can give. So here we can say that this is a unital algebra. A unital algebra. Here if you look at f of s equal to 1 for every s in S, this become a unit element in the algebra, hence it is a unital algebra. In fact, we can show that this is also commutative. This is a unital commutative algebra. Okay, so let us quickly look at one more example. Let us take, that is, K is compact subset of C. Look at C of K is set of all functions from K into C which are continuous. C of P is continuous on K. We know that whenever F is continuous on a compact set, it is bounded. So we can say that this is subset of B infinity of Kc. And with respect to all the operation that we have defined earlier, we can show that this is also an algebra. Not only algebra, a unital commutative algebra. So we can also say that it is a subalgebra of B infinity of Kc. So subalgebra means it's a subset, and with respect to the same operations of B infinity, it is independently in its own right, it is also an algebra. So that's why it is called a subalgebra. Okay, so let me quickly recall what we have done. Today we discussed about definition of a linear transformation and a few examples of linear transformations. Then we discussed that LV is a algebra. Then with that motivation we discussed what is an algebra and some properties of an algebra. With this I'll stop here. Thank you.